I see there are 22 students in the meet. Okay, but the form that I received from you is only 20. So means two students haven't filled up the form. Okay, I want to know, six of you, do you scan my Sejahtera just now? Yes, okay. Okay, I will start the class now. Okay, this week I cover about the CMOS circuit. Okay, not exactly a CMOS circuit, it is actually a resistive load inverter. Okay, one of the IC technology that use only one and most. Okay, I cover about the inverter. Okay, this inverter use only the NMOS, and then the some of the characteristics like DC characteristic uh, are discussed. Okay, the DC characteristic is about the voltage transfer characteristic VTC. Okay, and then also from there the VTC we can determine the noise margin. Okay, so about noise margin I have explained on Monday. Okay, I explained it on Monday. So I will continue with noise margin. Okay, this one, this slide. Okay, as you see in the slide here, there is a diagram. Okay, this diagram shows the input level and output level. Okay, there are four different voltage level as you see in the diagram. Okay, two is the input, two output. Okay, so all these voltages we call it as critical voltages. Okay, VIL, VIH, VOH, VOL. This is critical voltages. Okay, why call as critical voltages? Because all these voltages determine the noise margin of the circuit. We use these voltages to determine the noise margin, and then it also determines the performance of the circuit. Um, we can know how the circuit operate at different voltage level. Okay, so here you see the diagram. Uh, this is labeled as VIL, mean input low. Okay, and this is labeled as VIH, input high. Okay, and then this is VOH and VOL. Okay, what does it mean with this diagram? Okay, we can use this diagram, and then okay, we can understand this diagram by referring to the diagram that is having the three inverter. Okay, so this is the diagram with three inverter. You see that there is an input, output, input, output uh, for each inverter. Okay, so the input to the inverter must be correctly interpreted. Okay, in order to make sure that the output is correct. Okay, if the input, the voltage level is not correct, which means that the voltage level is fluctuated significantly, then the output will not interpret correctly. Okay, if I use this diagram to illustrate to you with the diagram, With this diagram, maybe you can see it better. Okay, I want to draw the diagram here. And maybe I just directly copy the diagram and paste it here. Okay, so that you can relate it easily with all the voltages. Okay, so take for example, assume that VIL is 2, the values here is 2 V volt, and VIH is 4.2. Okay, this is 5 volt and this is 0.5. This is as example. Okay, so in this diagram, the VIH, the value can be 4.2 and above. Okay, you see that here the VIH, the values here, this is the minimum voltage, 4.2 and above. So any voltage that is measured at 4.2 or above can interpret the output at the inverter. The output of the inverter can be interpreted correctly as a logic 0, okay, with an output law. Okay, and the VOL here, the value should be about 0.5 or below. Okay, or below. Because you see that the VOL, the voltage level, should be about 0.5 volt as label given here. Okay, this is below. Okay, 0.5 is the maximum, is the maximum voltage. Maximum voltage when the output is low. Okay, so when this signals with this voltage level is propagate to the input of the second inverter, so the voltage here is called as VIL. So the values of VIL must be within the range 2 or below. Okay, if the voltage is increased or amplified by the noise above 2 volt, okay, then the output will not be correct. Okay, so the noise margin here between the input law and output law, we take this. Okay, this is VIL, input law, and this is output law. So these two voltage, we can use them to determine the noise margin. Okay, this is for the raw noise margin. Okay, and then if we consider the high noise margin, okay, the high noise margin will be this. Okay, this is VOH. Okay, when the input is low, then of course the output will be high. Okay, this is output high, VOH. Okay, VOH is 5. Okay, and then the value can also be higher than 5 volt. Okay, so any values at the output with more than 5 volt is also accepted. Okay, so this output, when the signal is propagated from output to the third inverter, the input here is also must be with high voltage level. Okay, we call it as input high. So this is input high, the values that is allowed, okay, to be interpreted correctly by the third inverter is 4.2. Okay, so 5, initially it is 5 volt. Okay, if the output voltage is 5 volt, then when the signal is propagated to the input of the third inverter, the voltage that it can fluctuate to 4.2. Okay, there must be fall within a certain range. Okay, if it fall uh, to a large uh, um, if the output voltage fluctuate to become a very small value, then this third inverter cannot interpret the output correctly. Okay, so there is a noise margin, okay, or noise tolerance between the output and the input. Okay, so for this one, the high noise margin can be determined as VOH minus VIH. Okay, so it is determined by this 5 volt minus 4.2. Okay, if according to this diagram. Okay, so this is how we should understand noise margin, okay, using the inverter. Okay, so now I go to the next slide. Okay, noise margin is closely related to the DC voltage characteristic. Allows you to determine the allowable noise voltage on the input of gate so that output will not be corrupted. Okay, if the output is interpreted incorrectly, it means that the output has already been corrupted. Okay, next I will mention about the operations of the resistive load inverter. Okay, so all of you know how the inverter operates. Okay, but now I will mention further on the current. Okay, there is a current flow in this inverter. Okay, drain current and the resistor current. Okay, and also some of the calculations you also need to know. Okay, the calculations is based on the formula given. Okay, to calculate the VOL, VIH, uh, and VOH. Okay, as well as the VIL. Okay, the critical voltages. Okay, sometimes it will be given, but if it is not given, we can actually calculate. Okay, we can calculate them. Okay, so in this slide, okay, the basic structures of the resistive load inverter is shown in figure 5.7. The load consists of a simple linear resistor, RL. The power supply voltage of this circuit is VDD. Okay, so I show you the figure 5.7. So this is the structures of a figure 5.7 with a resistor. Okay, this is resistor. Okay, you directly know this is resistor, and then this is NMOS. Okay, that's why we call it as a resistive load, because the load is the resistor. Okay. Okay, the drain current ID of the driver transistor is equals to the load current IR, okay, in DC steady state operations. Note that the source and substrate terminals of the driver's transistor are both connected to the ground. Hence, VSB is equals to 0. Consequently, the threshold voltage of the driver transistor is always equals to VTO. Okay, so regarding to the drain current and the load current, okay, so if you refer to this figure 5.7, okay, this is the load current, okay, and this is drain current. Okay, and then just now mentions about the substrate to source terminal. Okay, so this terminal is the substrate to source terminal. Okay, VSB equals to 0. Okay, because this terminal is connected to ground. Okay, so this is 0. Okay, so this circuit it operates in 3 operating mode. Okay, the mode are cutoff, saturation, okay, and linear. Okay, so I will talk one by one. Okay, so this mode is based on the operations of the NMOS. Okay, this is operation mode of NMOS. Okay, mean this one. Okay, this transistor. Okay, so the operations of the NMOS is not difficult to understand. We all know that it start to operate when the input is high. Okay, and then it will cut off or it will be turned off when the input is low. Okay, so here in this slide, okay, it show you that you see here, uh, uh, it state that the input voltage when it is below the threshold voltage, okay, this VTO is a threshold voltage. Okay, the input is very low, and then it is lower than the threshold voltage. Then NMOS will not be turned on. Okay, it is off. That's why the operation mode here is called as cutoff. Okay, so when the NMOS is turned off, no current, no voltage drop across the load resistor. Okay, so you see here the IR and ID. IR equals to ID is equals to 0. Okay, because there is no current and no voltage drop. And then the V out, okay, we can expect that the V out will be high. Okay, and the voltage level, okay, it should be according to the VDD. Okay, we should refer to it as the VDD. Okay, so as stated here. Okay, sometimes we also can write it as equals to VOH. Okay, when the input is slightly increased, okay, this input is increased above the threshold voltage, okay, but still not very high. It is in between the threshold voltage and then the V out plus VTO. Okay, this one V out plus VTO. Okay, if there is some value, you will know. Okay, what is meant by this one. Okay, later maybe I will show you with the use of the diagram, the VTC diagram. Okay, but for this one, what you need to know is when the input voltage increase to between these two range, which is above the threshold voltage and below the V out plus VTO. Okay, then the NMOS start to operate in saturation. Okay, start to operate in saturation. Then there is a current flow. Okay, the current flow from VDD through the load and then through the NMOS to the ground. Okay, here the V out will start to drop. Okay, it start to drop. Okay, and then as given here, the formula, this is for the load current. Okay, the load current, it can be determined using this formula. Okay, this formula is with the variables of input voltage and then the threshold voltage. Okay, so when the input voltage is increased, then the output will decrease. Okay, if the input voltage is increased further to above the V out plus VTO, okay, means that V in can be equals to VOH or VDD. Okay, then the NMOS will operate in linear. Okay, it operate in linear. Then output voltage, of course, will decrease. Okay, it decrease to VOL. Okay, and then under this operating mode, the load current we also can calculate using this formula. Okay, so you see that different operating mode, okay, there are different formulas that we can use to calculate the load current. Okay, so this is the VTC of a resistive load inverter. Okay, this is the realistic one. Okay, realistic one. Okay, also we can call it as non-ideal. Okay, because from the slope we can see. Okay, so if based on this VTC of the resistive load, we can know what is the voltage level of the input voltage and output voltage. Okay, so here the table already show you the operating mode is in cutoff, saturation, and linear. Okay, we can relate this with this diagram. Okay, and you see this, the first conditions of the input voltage is below the threshold voltage. So here the below the threshold voltage is about 1. Okay, according to this VTC, the threshold voltage is 1 volt. Okay, and then the VIL maybe 1.2. Okay, VIH here 246. This is 2.6. Okay, and then this is 5 volt. Okay, this 5 volt VOH, the maximum voltage that is according to this VOH. Okay, so here the region where the NMOS is in cutoff should be this region. This region. Okay, we call it as cutoff. Okay, why? Because all the voltage that is below the threshold voltage, the NMOS is in cutoff. Okay, and when the input voltage is increased to between the VTO and V out plus VTO. Okay, now VTO we know the value is 1 volt. V out here depends at the point at which, okay, maybe V out refer to the VTC. Let's refer to VTC. Okay, for example, refer to VTC at point where the V in fall. Okay, so for example, the input voltage is above threshold voltage. Okay, so I take, for example, at this point, maybe I take V at this point, VIH. Okay, this VIH, the values here, V out, we follow this level. Okay, is also 1 volt. Okay, so now VTO is 1 volt plus V out is 1 volt. This is 2 volt. So 1 volt. Okay, so here the, am I correct? Let me see. And this is, okay, B in here is 2.6. Okay, 2.6. 2.6, this VIH. Okay, maybe I have to select the point where it is not at VIH. It should be below. Okay, it should be in between the threshold voltage and the VIH. Okay, I take another point and see. Okay, maybe I take this point at 2. Okay, at 2, then here roughly the values will be 2.8. Okay, so this is 2.8 plus 1, so it's 3.8. Okay, it's 3.8. So here input is 2 point, is 2. Okay, it is 2. Means that, okay, I show you the values because I want you to understand what is meant by Vout plus VTO. Okay, so you see that here the input voltage at 2, okay, is between the threshold voltage and then the Vout plus VTO. Here the Vout and plus VTO, the value is 3.8. Okay, how to get the Vout is actually based on the VTC where I get the Vout here. Okay. Okay, also same for this V in above Vout plus VTO. Okay, so it means the region at the bottom. So this is the region, okay, for linear. Okay, and then another region for saturation is here. Okay, this is saturation. Okay. Okay, now then I goes to the calculations of VOH and VOL. Okay, for VOH, okay, we can straight away know what is the values of VOH. Okay, usually VOH is VDD. Okay, it also means that the input is low. Okay, output high, then input is low. Okay, so the current will also be zero. Okay, the load current and the drain current will be zero. So this one you must remember. Okay, and then the calculations of VOL. Okay, this is about output low. Okay, when the output is low, then the input is high. Okay, the input high, it must be high and as high as VOH. Okay, so the input voltage is equals to VOH. Okay, this is V in equals to VOH. And then when the input is high, so the NMOS is in linear region. Okay, and then the load current. Okay, the load current here is about the currents that is flow through the resistor. So you see that there is a VDD. Okay, this VDD minus Vout divided by RL. It means the voltage drop across the resistor. Okay, this is VDD. At this point is Vout. Okay, and this is RL. So we can easily determine the voltage drop across the resistor. Okay, and then the formula to calculate the VOL. Okay, this is the formula. Okay, this formula is based on the derivations using the Kirchhoff current law. Okay, this why this is Kirchhoff, why using this Kirchhoff current law, because it is derived based on the load current. Okay, so this is actually a load current. Okay, from here. Okay, and then this one is also a load current. Okay. Okay, so this one is a linear region. So this one, how do we know? Okay, this one I actually show you in the previous slide before. Okay, if you refer to this slide, you see this one, it is actually follow this formula. Okay, so these two formula, they uh, can be used, okay, to further derive to get the VOL. Okay, so this is the formula. And then for calculations of VIL, okay, when the input is increased, okay, okay, this is when the input is very low, okay, it is low but above the threshold voltage. Okay, when the input is low but above the threshold voltage, we consider it as VIL. Okay, why is that? Because if you refer to this diagram again, you see that the VIL is actually above the VTO. Okay, so here the input increase more. Okay, um, when the input is low but it is above the threshold voltage, then the NMOS is in saturation region. Okay, and again, the formula that is used to derive to get the VIL formula, it will be this. Okay, this one. This is VIR. VIR is the load current. Okay, this one is also the load current. Okay, based on the formulas given here. Okay, this one. Okay, this is the formula. Okay, they are equals together. Okay, and then differentiate. Okay, with V out over V in to get the VIL formula. Okay, this V out over dV in, this is equals to 1. Okay, this is actually indicate the slope. We can make it to replace with -1. Okay, so eventually we get this formula. Okay, all the derivation, you don't need to really know how to derive it. Okay, I explained to you because I want you to know how the formula comes from. Okay, but when you study, you do not really need to know how to derive it. You just roughly understand that it's okay. Okay, so another formula is V out. Okay, this is V out. Okay, this V out is obtained, okay, based on the formula here. Okay, this, okay, V out here, the formula is actually based on this formula. Okay, there is a V out here. Okay, we do some arrangement in the formula, and then the V in here, V in must be substitute with this VIL. Then you will get something like this. Okay, this formula is for V out. Okay, now I goes to calculations of VIH. Okay, VIH is input height. Okay, this is input high, so the voltage level maybe is equals to VOH or less than VOH. Okay, and then the operations of the NMOS will be in linear region. Okay, in linear region. And then the formula here is also derived based on the load current. So you can see this is the method how it is being derived. Okay, and the formula here, okay, this is the formula that can get. Okay, okay, for VIH. Okay, but this formula can actually further represent without the V out. Okay, what I mean here is you see this formula VIH is equals to VTO plus 2 V out minus 1 over KNRL, right? Okay, if we want to replace this V out with K and RL, okay, we can replace the V out with this square root 2 over 3 VDD divided by KNRL. So the final formula will be this one. Okay, this is the formula to use. Okay, final formula. Okay, with Kn and Rl. Okay, some of the questions will give Kn and Rl. Okay, but not the V out. So you need to use this formula. Okay, and if some of the questions that they not give, they give V out, then have to use this one. Okay, but normally Kn will be given. Okay, Kn will okay, I just remember, okay, Kn usually you need to calculate. Okay, it will not be given. Okay, you need to calculate. The given one is K prime. Is with K prime. You will see this. Okay, there is a K prime and K. Okay, there are two different parameters here. Okay, it's not the same parameters. Kn and Kn prime is different. So Kn prime will be given. You need to use this K prime to calculate to get the Kn. Okay, to get the Kn. So this one I mentioned here. Okay, so later when you do your tutorial, you will understand this. Okay, so next is about the influence of KNRL. Okay, the terms Kn and RL plays an important role in determining the shape of the voltage transfer characteristic. Okay, if you see each of the formula that I show you just now, each has this term KNRL. Okay, you can see here, so this is KNRL, okay, in calculations of VIH, and also this is the calculations of VIL, the formula to calculate the VIL with this term. Okay, and also another formula is for VOL. There is also the KNRL. Okay, so this term is quite important. Okay, it plays an important role because it determines the shape of the VTC. Okay, KNRL appears as a critical parameters in expressions for VOL, VIL, and VIH. KNRL can be adjusted by circuit designer. VOH is determined primarily by the power supply voltage VDD. The adjustments of VOL receive primary attentions than VIL and VIH. Larger KNRL, okay, will cause the VOL become smaller and with large transition slope. Okay, there is a VTC here. Okay, this VTC, they are plot with three different KNRL value. Okay, so you see here the slope is different when the KNRL is larger. Okay, this is 8. Okay, the value is 8. Then the transitions here is larger. And then the values of VOL. Okay, the value of VOL usually we measure at this point at which there is a slope. Okay, let me check again. Okay, not the slope, it's at the VOH. Okay, so it's at the VOH. Okay, so this one is wrong. Okay, we should take at this point. Okay, this is 5 volt. Okay, 5 volt is the VOH. We should follow here. This is the VOH. Okay, so at this point, we can determine the VOL. Okay. Okay, I just estimate the values here. Okay, you need to take note of this one. The VOL here is the output law. Okay, output law means that the input is high. So it is obtained based on when the input is high. Here the input is at the 5 volt, the VDD. Okay, so for each of the VTC, we also can determine the VOL. Okay, and then the VIL and the threshold voltage. Okay, threshold voltage already given, it is 1 volt. Okay, VDD also given. Okay, so only the VIL and VIH need to determine. Okay, if a VTC is given to you, so you no need to use the formulas to calculate. You can straight away get the values from this graph. Okay. Okay. Here, assuming the parameters such as the power supplies voltage VDD and the driver MOSFET threshold voltage VTO are detected by system and processing related constraint. The term KNRL remain as the only design parameter which can be adjusted by the designer to achieve certain design goals. Okay, so now you know, okay, how the designer uh, manipulate the parameters, okay, to get the desired performance. Okay. Okay, now I will cover power consumption. Okay, power consumption is about DC power consumption. Okay, DC power consumptions, there is also an average DC power consumptions. Okay, so we consider it when the input is low and also when the input is high. Okay, when input low means the driver transistor is cut off. No steady state currents flow, then no DC power consumptions. Okay. Okay, when the input is high, both a driver MOSFET and the load resistor conduct a non-zero current. The output voltage VOL, so the current ID, this is the drain current, and the load currents, they are equivalent. Okay, this one is the formulas to get the current. Okay, this indicate the current. Okay, and then this is VDD divided by 2. Okay, why divided by 2? Because this is about to get the average DC power dissipation. Okay, if you want to calculate the DC power dissipations, it will be VDD multiply VDD minus V output law. Okay, divide by RL. Okay. Okay, there is another example. Okay, about the design of this resistive load inverter. Okay, these examples I take it from one of the reference book. Okay, okay, you see the questions given here. Consider the following inverter design problem. Given VDD equals to 5 volt, Kn prime equals to 30 micron ampere per watt square, and VTO is 1 volt, design a resistive load inverter circuit with VOL equals to 0.2 volt. Specifically, determine the width over length ratios of the driver transistor and the values of the load resistor RL that achieve the required Vout. Okay, how to determine the width over length ratio and the values of the resistive load RL? Okay, we have to use the formula. Okay, the formula that used to calculate the VOL. Okay, in these questions, VOL is given. VOL is 0.2 volt. Okay, so we have to use on the formula. Let me see. Okay, so the formula is given here. Okay, I will just mention this directly. Okay, in order to satisfy the design specifications on the output low voltage, we start our design by writing the relevant current equations. Note that the driver transistor is operating in the linear mode when the output voltage is equals to VOL. Okay, and the input voltage is equals to VOH. VOH is equals to VDD. Okay, so this formula is the formula that used to obtain the VOL. Okay, initially the formula is like this. Okay, VDD minus Vout RL equals to K divided by 2. Okay, and then 2 Vout. Oh no, this is not Vout, this is Vin. Okay, this is Vin minus VTO multiply with Vout minus Vout square. This is the initial formula. Okay, you can refer back to the last few slides. Okay, so this is the formula. After we substitute the Vout with VOL, it become like this. Okay, and the Vin substitute with VOH since the input is output high. Okay, the voltage level is as high as the VOH. Okay, so here you see that this is output H. Okay, I mentioned this to you because I don't want you to be confused. Now I clarified to you. Okay, I mentioned to you so that you know what is meant by this. Okay, this is the Vin. Okay, the input voltage is equals to VOH. That's why here this is VOH. Okay, and then the VOL, this is actually about the Vout. Okay, this one also. Okay, so all the value is given except not VOL, except what? Except the width over length and then the RL. Okay, one more thing. This is K, right? I want to mention about K. Okay, K, and you see this is K prime. Okay, they are related as K equals to K prime multiply with W over L. Okay, this is width over length. Okay, so always the questions given the K prime, not the K. So if you want to know what is the value of K, then you have to calculate, okay, using these two value. Okay, now the values of width over length is not given, so we have to determine ourselves. Okay, so here you see this formula is obtained. Okay, it is being substitute with all the value, and then this is the formula. Okay, this is the formula. Okay, this formula we can determine the width of length ratio and then the load, okay, the resistor, the values of the resistor. Okay, okay, how to determine? Okay, later there is a table shown in the next slide. Okay, this is the table. Okay, you see this table listed with the values of the width over length 1, 2 until 6. Okay, and then the load resistor is kilo ohm. Okay, this is the value. Okay, how to get this value? Okay, we need to use back this equation. Okay, this equation is 2.605. Okay, I write here. The formula is R over L multiply RL. Not R, it's W. This is W over L multiply RL equals to 2.05 multiply 10 power 5 ohm. Okay, if we do the assumption, the width over length is 1 until 6. Okay, means that we can use this formula to replace width over length with the value from 1 until 6. Then RL, we can know what is the value. Okay, so you see this when the width over length ratio is 1, then the load resistor will be 205 kilo ohm. It is actually based on this formula from here. Okay, and then for the rest of the values here is also from this formula. Okay, after the width over length is determined. Okay, from here we can determine the DC power dissipations using this formula. Okay, since here this is about average, okay, it's about average power dissipation, so you need to use this formula. Remember, there are two formula. Average must be divided by 2. Okay, so with the RL value, then you can get the power consumptions. This is the values for all the load resistor. Okay, from this table, there are some conclusions we can get. Okay, the load resistor, when the load is high, then the power consumption is low. Okay, and then when the load resistor is small, the value is small, then the power consumption is high. Okay, so when we choose one that is suitable for the inverter design, we need to choose the one that has a lower power consumptions. Okay, so there is a statements given here. Okay, power consumptions increase. Power consumptions increases significantly as the values of the load resistor RL is decreased and the width over length ratio is increased. If lowering the DC power consumption is the overriding concern, we might choose a small width over length ratio, okay, and a large load resistor. Okay, a large load resistor can have a low power consumption and also a small width over length ratio. Okay, so to select, then this one should be select. Okay, with high values of load resistor and low power consumptions. This has the lowest power consumption, and then the width over length also small. Okay, but when we choose this, there is also other considerations. Okay, so here on the other hand, if the fabrications of the large load resistor require a large silicon area, clear trade-off exists between the DC power dissipations and the area occupied by the inverter circuit. Okay, so just now I say that choose this one will be better because with lower power consumptions, but there is another drawback, which these high values of load resistor, okay, it will take more space to fabricate on the chip. Okay, so here you see fabrications of the large load resistor require a large silicon area. So this is the trade-off. Okay, the trade-off means there is a good side, there is a negative side. Okay, I see it's about time to take a break now. Okay, I think I will finish this, then we take a break. Okay, so the chip area occupied by the resistive load inverter circuit depends on two parameters: the width over length ratios of the driver transistor and the values of the resistor RL. The area of the driver transistors can be approximated by the gate area, assuming that the gate length L is kept at its smallest possible values for the given technology. The gate area will be proportional to the width over length ratios of the transistor. The resistor area, on the other hand, depends very strongly on the technology which is used to fabricate the resistor on the chip. Okay, so when we want to consider the chip area, okay, for this case, when we consider the resistive load inverter, okay, we need to know the area that occupied by the resistor. Okay, so there are two values here. Okay, since in resistive load inverter there are one resistor and one transistor. Okay, so the transistor, the size is determined by this width over length. Okay, and then the size of this resistor, the area occupied by this load resistor, is determined by its resistance. Okay, so the higher the values, then the larger the area that it will occupy on the chip. Okay, okay, next, there are some technology that can actually help to solve to fabricate a smaller size of the resistor as the load. Okay, so this one I will mention after the break. We take a break now. Okay, as usual, the break will be about 10 minutes. Okay, I will continue my lecture now. Okay, now I will further discuss about the fabrications of the resistor on the chip. Okay, if according to the slide here, there are two possibility of fabricating the resistor using the standard MOS process. Okay, one is a diffuse resistor and another one is the polysilicon undoped resistor. Okay, the diffuse resistor is fabricated as an isolated N-type or P-type diffusion region with one contact on each end. The resistor is determined by the doping density of the diffusion region and the dimension. Okay, for example, the length to width ratios of the resistor. Okay, there is a diagram here which show the diffuse resistor. Okay, the layout design of a diffuse resistor. So this is the layout design of a diffuse resistor as a load. Okay, in a resistive load inverter. Okay, you see that this is the layer. Okay, that is used. Okay, we actually call it as a diffusion region. Okay, this is diffusion region. Okay, doped with some dopant. Okay, and then this one is connected with two contact. Okay, there is one with uh, connected to the VDD, another one is to the output. Okay, so here we'll further describe on on these two. Okay, just now mentions there are two MOS process. One is the diffuse resistor, another one is the undoped poly resistor. Okay, practical values of the diffusion region sheet a resistor. This is resistant. Okay, range between 20 to 100 ohm square per square. Okay, consequently, very large lengths to width ratios would be required to achieve resistor values on the orders of tens to hundreds of kilo ohm. Okay, if we want to fabricate a resistor, okay, we need to use a correct material, okay, to for fabrications as a diffusion region, okay, and then the doping, okay, determines the resistance, okay, of the diffusion region. Okay, this is the informations about the diffuse resistor. Okay, next is about the uh, polysilicon resistor. Okay, this polysilicon resistor is undoped. Okay, means that the polysilicon is used to fabricate to form the resistor. Okay, this one there is about the placement. Okay, now I refer to this statement. The placements of these resistor structures on chip commonly in shape. Okay, this is this is I'm not sure what is this. This shape, what shape is it? You need to check. Okay, type in a website. Okay, you need to search. Okay, online. What is this shape about? Okay. Okay. So the placements of this resistor require significantly more area than the driver MOSFET. Okay, as illustrated in Figure 510A. Okay, a resistive inverter with a large diffuse load resistor is therefore not a practical components for VRSI applications. Okay, so this is the figures that mentioned. Okay, so this one as you can read just now, okay, this resistor load circuit that is with the diffuse resistor is not suitable to be used in VLSI applications. Okay, so next I will explain about this undoped polysilicon resistor. Okay, an alternative approach to have silicon area is to fabricate the load resistor using undoped polysilicon. In conventional polygate MOS technology, the polysilicon structures forming the gates of transistor and interconnects are heavily doped in order to reduce the resistivity. Okay, this is about conventional polygate MOS technology. Okay, by the name here, it is undoped polysilicon. It should mean that the polysilicon is not doped with any dopant. Okay, but in conventional polygate MOS, okay, it is doped heavily, okay, in order to reduce the resistivity. Okay, normally the resistivity of the doped polysilicon's interconnects and the gates is about 20 to 40 ohm per square. Okay, if sections of the polysilicons are masked off from this dopant step, on the other hand, the resulting undoped polysilicon layer has a very high sheet resistivity in the order of 10 mega ohm per square. Thus, very compact and very high value resistor can be fabricated using undoped poly layers. Okay, one drawback of this approach is that the resistance value cannot be controlled very accurately, which result in large variations of the VTC. Consequently, resistive load inverters with undoped poly resistor are not commonly used in logic gate circuit where certain design criteria such as noise margin are expected to be met. Simple inverter structures with large undoped poly load resistor are used primarily in low power static random access memory. This is about the static RAM, okay, where the primary emphasis is on the reductions of the steady state of the power consumptions and the operations of the memory circuit is not significantly affected by the variations of the inverter VTC. Okay, so it looks like the undoped polysilicon is more suitable to use in current technology, okay, to fabricate the load resistor. Okay, if refer back to this figure, if you compare these two resistive load inverter, you will see that this undoped poly resistor, it occupied a lesser area than this diffuse resistor. So this one is more uh, suitable, okay, to be applied. Okay, but there is some of the negative effect, okay, uh, that has to consider. Okay, that is the resistance. Okay, that is being measured from the polysilicon. Okay, has large variations. Okay, it has large variations as mentioned here. Okay, but these variations does not have any effect, okay, to the power consumptions. Okay, in a CMOS circuit, we have to prioritize the power consumptions. We need to make sure that the power consumption is low. If not, then it will cause the breakdown of the circuit. Okay, so if for this purpose, this is for the low power cell. Okay, the undoped polysilicon resistor still can be used in this application. Okay, so that is about the fabrications technology of the resistor. Okay, now I will go to discuss and cover this current voltage characteristic. Okay, this is about current and voltage of the animals. Okay, sometimes we call it as a load. Okay, not load. Okay, what I want to mention is there is a load curve. Okay, later I will show you that describe the current and then the voltage of the resistor. Not resistor, it's transistor. Okay, so okay, now you see that in the current slide, this is about the drain current. Okay, this is drain current. Drain current is equals to 0. Okay, just now I mentioned when the drain current is 0 means that this is in which mode? Okay, already stated here. I actually want to ask you, but I think the answer is already here, so no point I ask you. Okay, so it is in cutoff. Okay, so when the NMOS is in cutoff, so the drain current is 0. No drain current, no load current. Okay, so you need to always remember this. Okay, now I goes to the next. Okay, this triad. Okay, this is another term, triad. Okay, this is actually means the linear region, linear mode. Okay, linear mode. Okay, sometimes triad, this term is used to represent it as linear mode. Okay, when in triad mode, the drain current is dependent on both VGS and VDS. Okay, so you see this is the formula, drain current formula. Okay, this is VGS, VDS. Okay, the formula here is the same. Okay, they look similar to the ones that I showed you just now for load current. Okay, load current, if you compare, the formula is the same, except that this VGS, okay, is used and VDS is used to use these two parameters are used in this formula. Okay, this VGS, this is actually the V in. Okay, V in equals to VGS. This is get to source voltage, and VDS is V out. Okay, so this one also again, K prime multiply width over length, it is K. Okay, this equation is valid for both NMOS and PMOS transistors. Okay, if both are in triad mode. Okay, recall that for PMOS devices, the values of VGS and and VDS are negative. Okay, but note that this will result in a positive values of ID. Okay, so this one you also must take note. For PMOS, the VGS and VDS are negative. Okay, means that if the input voltage VGS is equals to 1 volt, this is to the NMOS. Then if the VGS to the PMOS is of the same value, okay, then you have to know that the value should be the same, but the sign here should be negative for PMOS. Okay, and the currents, if we substitute these values to the formula here, the current we will get a positive value. Okay, now I will go to saturation. Okay, saturation, this is the formula to calculate the drain current. Also the same with the load current. Okay. Okay, this one I think I not need to explain again because it's a similar one. Okay, and this one summarize all the drain current in 3 different modes. okay, with all the conditions of the input voltage. Okay, so all three are listed here, so you can refer directly to this. Okay, next. Okay, this is the curve. Okay, IV curve. Okay, usually we also can call it as load curve. Okay, so this curve we label it. Okay, so if you refer to this curve, you see that this is the drain current. This is the VDS. VDS means the output voltage. Okay, so here there are different line in the curve. Okay, the blue line here is of different input. VGS is different input. Okay, this is of 10. VGS equals to VT plus 2. 2 is from where? It's actually the values that we assume. Okay, so this 2 indicate the VDS. Okay, the VDS. Okay, this is from this. Okay, VDS equals to VGS minus VT. So when we want to determine VGS, then we straight away knows that VGS is equals to VDS plus VT. So this is with different input voltage. Okay, so in this curve, okay, what does it mean by this curve here? Okay, this curve that is at this level 0, the current is 0. Okay, at this level it means that the ID is equals to 0. Okay, when ID is equals to 0 means that the NMOS is cut off. Okay, so you see the line here, this is the line, it is indicated as cut off, and then the input voltage is below the threshold voltage. Okay, and then when the input voltage is increased higher and higher, you see the curve here, the shape of the slope here will be large. Okay, this region, you see this region where the line here is increased, not the line, okay, I should say that the current is increased proportional. Okay, this region is where the NMOS start to operate linearly. Okay, so this region, it is called as triode region. Okay, and then here, the region here, you see that the line here is constant. Okay, at different input voltage, the line is constant. So it means that there is no increased current. Okay, the current is saturated. Okay, saturated because current cannot go higher. Okay, so it stay constant. So this one, we call this region as the saturation region. Okay, so this is how you should understand the load curve. Okay, so another load curve, this is also a load curve. Okay, this load curve explain to you what does it mean by the curve here. Okay, so at this line, this region, it is almost a straight line, okay, with a slope proportional to VGS minus VT. Okay, and then this curve start to bend because the channel resistor increases with VDS. Okay, the drain current cannot go higher at this point. Okay, it start to saturate, it become constant. Okay, so this region again is called as saturation regions. The current saturate because the channel is pitched off at the drain end, and VDS no longer affect the channel. Okay, for PMOS, the drain currents can also be calculated. Okay, the value, not value, this is the formula. Okay, the formula here is almost the same for NMOS except that the conditions of the input voltage is different. Okay. Okay, so this one you can compare. Okay, compare with NMOS. Okay, you can roughly get what is meant by the conditions given here. Okay, all polarity for this load curve for PMOS. Okay, when we plot a load curve for PMOS, okay, all the values will be negative. Okay, all the values will be negative and all the polarity are reversed from NMOS. Okay, the drain current, okay, this is about drain current, enter source and leave through drain. Pole mobility is lower, then means that it is with low transconductance. Okay, and most favor over PMOS. Okay, just now I shown the load curve for NMOS. Okay, it looks like this. Okay, this is for NMOS. Okay, but for PMOS, okay, for PMOS, we can also plot it in this way. This is ID, this is VDS. Okay, it can be drawn like this. Okay, at different levels of input voltage. Okay, and then also the drain current also uh, uh, like this. Okay, the value may be the same, but the polarity will be different, will be in negative. Okay, this is negative VDS. Okay, okay. Again, I'm repeat. The load curve for PMOS will be in opposite to the NMOS. Okay, the curve looks similar like this. Okay, so as summary, um, this is the last slide for this resistive load inverter. So in summary, this is all the formula that is related to the calculations of all the voltages uh, for resistive load inverter. Okay, this one all listed here is for you to refer easily. Okay. Okay, I see that I still have time, means I can go to the part 2. Okay, before I go to part 2, do you have any question you want to clarify on this topic? Okay, if no questions, then I will directly go to part 2. Okay, I hope all of you are able to follow here. Okay, if you cannot follow later when you do the revisions, you can refer to the video. Okay, I will upload the videos to the classroom. Okay, this is also of the same chapter, similar topic. Okay, in this static characteristic part 2. Okay, it is also about MOS inverter. Okay, just now I show you the resistive load inverter. Okay, now there is another type of inverter. Okay, I will introduce to you another two type of inverter. Okay, and also you will study about the DC characteristic of these two inverter. Okay, okay. In the previous topic, the resistive load inverter use is the resistor and then the NMOS. Okay, but a resistive load inverter looks not so suitable to be used in VLSI system applications. So that's why this topic is introduced to you, okay, with another types of the MOS inverter to show you which inverter are more suitable to be used, okay, in VLSI application. Okay, so as the the start, okay, for this topic, okay, you can refer to this slide. The simple resistive load inverter circuit discussed previously is not a suitable candidate for most digital VLSI system applications, primarily because of the large area occupied by the load resistor. Okay, the inverter circuit, which use an NMOS transistor as the active load device instead of the linear load resistor, will introduce. Okay, this means that later you will see the load resistor, okay, will be replaced with an NMOS transistor. Okay, the transistor will be used as the active load device. Okay, the advantages of using a MOSFET as the load device are the silicon area occupied by the transistor is usually smaller than that occupied by a comparative resistive load. Okay, and it can be designed to have better overall performance. Okay, so these are two figure. Okay, we call it as enhancement load NMOS inverter and depletion load NMOS inverter. Okay, so this is another type of NMOS inverter, a NMOS inverter other than resistive load inverter. Okay, so for this one, enhancement load NMOS inverter. Okay, there are two NMOS transistor. Okay, so you see that this is NMOS transistor as the load. Okay, and also this is NMOS transistor. I erase again. Okay, this NMOS as the driver transistor. Okay, two NMOS are used in enhancement load NMOS inverter. Okay, so you see this figure here. It is quite similar to the CMOS inverter. Not similar. Okay, it is uh, not similar actually. Okay, just some of the connection is similar. Okay, in this NMOS inverter, only NMOS transistor are used. Okay, NMOS transistors can also use as the load. Okay, you see the connections here. The input to the NMOS, the load NMOS is connected to the VDD. Okay, so the source here. Okay, this is source. This is drain. Okay, here the source terminals of the NMOS should be is connected to VDD. Okay, should this be the source? It should be drain. Okay, because a source of the NMOS. Okay, this one have to check. You all have to go and check. Okay, but you see that the connections here is similar to the connections like the TMOS. Okay, so here there is a load current and also drain current. Okay, and then you see that this is the source to subtract terminal that is equals to 0. Okay, so these two terminal, okay, these two terminals they are connected to the ground, so it is 0. Okay, this inverter circuit is with a saturated enhancement type. Okay, and also this is another inverter called the linear enhancement type load. Okay, how to differentiate? Okay, you see that here the load, you see the load NMOS, the input connections is a bit different than the one in this saturated enhancement type. Okay, the input voltage is connected to another source. Okay, this one I cannot see it clearly here, but I assume it as VGG. Okay, but I'm not sure. This one I have to go and check to verify. Okay, but what you can know is this is another supply voltage. Okay, so the input voltage is not supplied by the VDD. It is by different supply voltage. Okay, and others is similar to this one. Okay, the only difference is the input to the load and MOS. Okay, so this is two inverter circuit for enhancement load and MOS inverter. Okay, which you need to know how to differentiate. Okay, based on the structure given here. Okay, and about the depletion load and MOS inverter. Okay, this is a depletion load and MOS inverter. Both of these. Okay, this is A. Okay, A is inverter circuit with depletion type and MOS load. The input to the NMOS here is connected to this, which is connected to the output. Okay, they are of the same load. So here, as I see here, okay, they are connected to the output. This line, okay, the input to the NMOS. Okay, and then the input to the NMOS of the driver. This NMOS is the driver transistor. Okay, so the input is equals to VGS. Okay, it is quite similar to the enhancement type. Okay, also the difference is in here. Okay, the input to the load and MOS. Okay, so you see here this circuit can be simplified and represent in this way. Okay, Okay, this is a simplified equivalent circuit consisting of a nonlinear load resistor and a non-ideal switch controlled by the input. Okay, so this nonlinear resistor, even though it is draw as a resistor symbol, this is a resistor symbol. Okay, it is actually uh, the load and MOS. Okay, and then this is a switch. Switch means this is the driver transistor. Okay. Okay, about the enhancement load and MOS inverter. Okay, it depends on the bias of voltage applied to its gate terminal. Okay, it operate in two operations region. Okay, the transistor. Okay, the transistor here is referred to the load transistor. It can be operated either in the saturation region or in the linear region. Okay, the saturated enhancement load inverter in figure 5.11a, this is the figure that I showed you just now. Okay, it requires a single voltage supply and a relatively simple fabrication process. Okay, yet the VOH level is limited to VDD minus the threshold voltage. Okay, the single voltage supply here means the voltage supplies of VDD. Okay, this one you can see in the figure given. Okay, for linear enhancement load inverter in figure 5.11b, is always biased in the linear region. Okay, thus the VOH level is equals to VDD, resulting in higher noise margin compared to saturated enhancement load inverter. Excuse. Okay, so here looks like the linear enhancement load inverter perform better than the saturated enhancement load. Okay, because linear enhancement load give a higher noise margin. Okay, if we want to evaluate the performance, higher noise margins will be better. Okay, however, okay, this enhancement load in MOS inverter is not suitable to be used in any large-scale digital applications due to high standby power dissipations. Okay, now next is about depletion load and MOS inverter. Okay, it consists of a non-linear resistor and a non-ideal switch. Okay, this switch means the driver transistor. The driver device is an enhancement type NMOS transistor with the threshold voltage above 0. Okay, whereas the load is a depletion type NMOS transistor with the threshold voltage below 0. Okay, so just now the figure already show you, okay, with two NMOS in the depletion loop inverter. Okay, one is the enhancement type, another one is the depletion type. Okay, even though two are NMOS transistor, but their threshold voltage are different. The gate and the source node of the load transistor are connected. Hence, VGS load is equals to 0 always. Okay, so I goes back to the figure. So it mentions that the gate and the source node of the load transistor are connected. Okay, so it means that this is gate, this is source, this is drain. Okay, already stated here. So this one also need to change. This one is drain and source. Okay. Since the threshold voltage of the depletion type load is negative, the conditions VGS load above the threshold voltage is satisfied. And the load device always has a conducting channels regardless of the input and output voltage level. Both the driver transistor and the load transistor are built on the same P-type substrate. Okay, since it is NMOS, okay, the substrate is a P-type substrate. Okay, and this substrate is connected to the ground. Consequently, the load type is subject to the substrate bias effect. So that is threshold voltage is a function of its source to substrate voltage, which means that the VSB load is equals to V out. Okay, this one also can refer back to the figure. Okay, let me see. I have 5 minutes left. Okay, okay, maybe I cover another 2 more slides then I stop. Okay, this table compare between enhancement load NMOS inverter and the depletion load NMOS inverter. Okay, the comparison here are made based on the advantages and disadvantages. Okay, for advantages, the enhancement load NMOS inverter has high noise margin. Okay, this one is for the linear type. Okay, you must remember this one is for linear type. Okay, enhancement type does not have this high noise margin. This is for linear type. Okay, this is the only advantages in enhancement type NMOS inverter where it is operated in linear. Okay, okay, for depletion load, okay, the advantages there are 3. Okay, and also this depletion load type can overcome several disadvantages of enhancement load NMOS inverter. Okay, the advantages, this is one of the advantages. Other advantages are the sharp VTC transitions and better noise margin, single power supply, smaller overall layout area. Okay, and then the disadvantages for enhancement load. Okay, the fabrication process is slightly more complicated and require additional processing step, especially for the channels implant to adjust the threshold voltage of the load device. Okay, and another disadvantages is enhancement load use two separate power supply voltages. Okay, and suffer from relatively high standby DC power dissipations. Okay, for depletion load, okay, the disadvantages that that can be identified is the fabrication process. Okay, fabrication process is also more complicated. Okay, the it also require additional processing steps. Okay, this is the only one. The only one disadvantages that by this depletion load inverter. Okay, other disadvantages is not stated here. Okay, as I have read and studied from one of a reference book, this is the only disadvantages that I can determine. Okay, so this one you need to study, okay, and understand. Okay, this topic also is quite important. Okay, uh, question may come out from this topic. So this you will have to know uh, the difference of the structures, advantages and disadvantages. Okay, I see that now is almost 4. I think I stop here. I cannot cover another one slide. This is the slide that I actually want to cover, but seems like I don't have enough time. Okay, so I think I will stop here. Okay, your attendance, no problem. So if no further questions from you, then we can dismiss now. Okay, thank you.